So far, what we've done is that we've developed a reasonably extensive method based on the operators to solve the system and evaluate them, right? Now, operators are good and nice because they're quite general. There are not very many assumptions about the kind of functions you can deal with them and all those things, but they are, at the end of the day, operators. So it would be nice to go to things that are more like functions. So now what we are going to do, we are going to go and develop the concept of transfer functions. And you will see, once you know the operators, essentially a transfer function is a pretty straightforward response and pretty straightforward development. So here's what we are thinking about. So we are talking about system functions or transfer functions. You could argue that we've done the necessary hard work to develop the foundation to get to this point, and now it becomes relatively easy to apply it and take advantage of what we've developed, the investment we've put into it. Okay, so let's say you have a system, but now let's say your input is a special input. So let's say your input x of t is e to the st u of t, where s is a complex number, and you can write it as sigma plus j omega, where this is the real and imaginary part. Sigma omega are this real and imaginary part. Right? So let's say you start with a system like that, and you hit it with an input that's of e to the st, which is a complex. Now, this is basically the notion of complex frequency, really. This captures, these kind of inputs subsume the cosines and sines, because you can make cosines and sines off of a pair of these, right? We saw that. We can basically write them as e to the x plus e to the negative x over 2, or e to the x minus e to the negative x over 2j, etc., etc. It also subsumes the exponentials, the regular exponential, or more combinations of those, basically exponentially decaying or exponentially growing sines and cosines. So this is a useful thing to look at, because we saw that because of the fundamental theorem of algebra, the system responses would really fall into combination of these. Because when you factor them, when you do partial fraction expansion, you will either have first or second order polynomials with real coefficients in the denominators of your elements, and they can only produce these kind of responses. So this is a useful and pretty powerful thing to do. So if I hit a system with that, if I use the methodology that I had, so how can I express x of p? What is the x of p associated with this? Or I can write this as x of p operating on delta of t. What is that x of p that generates this off of a delta of t? We already know the answer to this, right? It was part of our catalog. You remember e to the rt, or negative rt. What was e to the negative rt u of t? What generated e to the negative rt u of t off of a delta? 1 over p plus r. So this would become what? 1 over p minus s. Exactly. Right? Delta of t. So that's the input that would produce that. So now if I wanted to know what the response of the system to this is, essentially, what I have is, you can write it as y, or write as y of t is going to be h of p operating on x of p operating over delta, which is going to be h of p over p minus s delta of t. Right?
So is x of p 1 over p minus s, or 1 over p minus s on delta?
X of p, no, yeah, you're right. This is x of p. Thank you. There's no delta. If this were x of t, that would be right. Thank you for clarification. So now we are going to make one assumption here. So I'm going to assume that there are no roots of p equals s in the h of p. So in other words, I'm assuming that the denominator of h of p does not have a root of p equals s. Right? So I'm saying that there is no inside this. If you look, this thing has some property, right? So I'm just assuming that the denominator, if you have this like a bunch of polynomials multiplied, none of them is a p minus s, or a power of that. inside h of p. Okay? So I'm just making that assumption. And we'll see what happens. So if that's the case, then I can do a partial fraction expansion for, I mean, I can always do partial fraction expansion as long as h of p is a rational function. But then I would know what my partial fraction expansion looks like if I don't have anything like that. Because then I would be having some k over p minus s plus, and let's forget about the delta. I just should have, you know what? Let's just get rid of this delta and this delta and make this y of p. Because that just carries around and doesn't do anything good for me right now. So that plus some other, whatever is left when you divide it by that, right? When you divide it by that, there would be the rest of the partial fraction expansion. I'll show that as y sub n of p. And we'll see why I use the sub n part. So what is this response? What is y of t like? So if you look at y of t, then it would be what? It would be this k times the response associated with 1 over p minus s. If I were to do this partial fraction expansion, how would I calculate this k? I mean, what was our methodology? What was our approach? The way we calculated k was that we multiplied the function, right, by the polynomial that we were looking at. You had it in the denominator. So in essence, you would multiply it by p minus s, whatever you had, this thing. And then you replaced it with a root. So basically, you would just take the p's and replace them with s. That's what we did, right? But when you do this, this has become something pretty straightforward, right? Because these two cancel. So what that means, it's basically h of p, where p is replaced with s, which we will show as h of s. Now, this is a function, right? We've just put this is a real function. This is a function of s. It's a function of a complex variable. This is called a transfer function or a system function. And we'll see why it's important. Why is this important? Because now if I look at the response of this, what is y of t? Y of t is going to be this operating on a delta, right? Plus this operating on a delta. What is this operating on a delta? Well, I know k is h of s. And then what is the response of a system with an operator 1 over p minus s? Right? E to the st u of t plus whatever this is operating on delta of t, which I show it with y sub lowercase y sub n of t. So this is important because what is this? So now forget about all the derivation. Look at this result. So saying that I had an input which was e to the stu of t. The system produced an output that has two parts. One part, which is e to the stu of t, with some coefficient weighted by some function h of s, and then some other part. Now, can you guess why I used the subscript n here for that? What does that n stand for? Natural. And what is this? Forced. So this is the forced response, and this is the natural response of the system. So it says the forced response of the system is just what you hit it with some coefficient, with some weight. So if I hit it with some sinusoid, I'm going to get that sinusoid, for example, but it may get amplified or it may get attenuated. It will have some phase shift because these are complex functions in general. But all of that is captured by this h of s. So if you want to know what the system does to the forced response of the system only, if you don't care about this natural response, if you're only looking at that forced response, there's a very easy way to calculate it. It says all you need to do at that complex frequency you are hitting it with, evaluate the system function, which is the system operator where you take the p and replace it with an s as a function. right? So let me give you an example to make it. So the weighting of the system, of the forced response is really determined by the system function. System function is the weight of the forced response. How much larger or smaller does it become? And it depends on the system. So let's do an example. So let's say I have a differential equation. Okay. So I have let's do it as a differential equation. Y double prime plus 3y prime plus 2y equals x prime plus 3x. And let's say x now first is e to the negative 4t u of t. So this definitely falls in the general category of e to the st, right? Because this is what is s in this case? Negative 4, right. So I'm trying to find the response to the system. So first I need to find the system operator and system function. So the system operator, of course, you can write it as p squared plus 3p plus 2y. And this is basically p plus 3x. So you can write y as hp over x, which is basically p plus 3 over p plus 1 times p plus 2. And therefore, the h of s, where the system function is basically you take the operator and convert it to a function, is this. Right? So far, everything should be clear. If it isn't, let me know. Now, you have that, and then now you want to find what's the response to this thing. So what is the response? I know that if I ask you, what is the forced response? If I'm only interested in the forced response to this. So what is the yf of t of this thing? It should be pretty straightforward to calculate, right? What do? You calculate h, in this case, h of negative 4, this function for negative 4, and then multiply it by e to the negative 4t u of t. That's your input. That gets multiplied by h of negative 4, which is what? This is negative 1, negative 3, negative 2. So it's negative 6, 1/6, right? So it's negative 1/6 e to the negative 4t u of t. I believe that's what it is. Yeah. So you can the strength of the system function, right? Sometimes it's called transfer function, but transfer function is a more special case. The significance of a system function is that it allows you to directly find what the forced response is for different frequencies. So it captures the forced response of the system at all frequencies. So if you look at this function, you know what its forced response is to all frequencies. Almost all frequencies. Why do we say that? Okay, well, let's just try a different frequency. So this is like first example. So let's say another x e to the negative 4t. Negative 3t this time, u of t. What is its response to that? So how do I calculate it? Same deal, right? So what's the forced response? Is h of negative 3 e to the negative 3t u of t. So what is h of negative 3? What is it? 0, right? If I put negative 3 here, it's the root of the numerator. It's 0. The forced response is 0. What do you think these frequencies are called? That the root of the denominator, roots of the numerator, roots of the numerator. What do we call them? Zeros. Zeros of the function. The natural frequencies are the roots of the denominator, which are called poles of the system. So we'll talk about poles and zeros, right? Poles are the roots of the numerator, but there's a reason we call them zeros. Because the forced response becomes 0 at that frequency. It's a frequency at which, if you hit the system, its forced response is 0. It's completely desensitized to it. It's something that you're completely desensitized to as a person, if you want to use the person's analogy. Absolutely does not register. Air. Most of the time, they're not completely desensitized to it. When you swim, you're sensitized to it. All right. So now what if, okay, so that's good. And if I wanted to find the solution to this, though. No, but is that the full response? No. What is the full response? How do I calculate the full response? If I wanted to know the full response to this frequency, does it mean the system doesn't produce any response? No. The forced response is 0. But it has other responses. So if I ask you what is the response of the system, how do we calculate it? If I say this is my input, this is my system, how do we calculate I mean, you already know this, right? How do we calculate the response of the system? If this is the input, this is the system, catalog. Right? So from catalog perspective, what does this correspond to? What is the x of p associated with this? 1 over p plus 3. Right? So it's this operator operating on that. So it basically becomes that p plus 3 over p plus 1 times p plus 2. So that's h of p times x of p, this cancels that. So you have 1 over p plus 1 plus, times p plus 2. So if I want to find what the response of the system is, how do I do that? If my x of p times h of p is 1 over p plus 1 times 1 over p plus 2, I do partial fraction expansion. So the partial fraction expansion for that is going to be something over p plus 1 plus or minus something over p plus 2, which is what? For p plus 1, it would be this, evaluated for p equals negative 1 would be 1. For p plus 2, it's this, evaluated for p equals negative 2, which would be negative 1. And once you have that, what is the response? What is y of t? Overall response? Catalog? E to the negative t u of, or you can just minus e to the negative 2t u of t. Right? So what's happening? So this, one thing that's important is not to let the insight be lost in the math, right? Or in the algebra in this case, right? Just what is the insight? The insight is that you had a system, you hit it with e to the negative 3t, but because this was a special frequency for this system, it was one of its zeros, it did not produce any forced response at that frequency. It doesn't mean it doesn't have any response. It does have its natural response. You saw its two natural frequencies. You see both of its natural frequencies. But you don't see that particular input frequency. Now, if I had done this for the first one, e to the negative 4t, if I had multiplied this by e to the negative 4t, so I would have had to multiply this by 1 over p to plus p, 1 over p plus 4, right? If I wanted to calculate its output to this input. Now, this doesn't cancel that. So then I have a different partial fraction expansion, which would produce this frequency, and that frequency, because there would be three terms in that partial fraction expansion. It wouldn't produce this. It wouldn't produce the zero frequencies. Zero frequencies are not natural frequencies of the system. But it does produce the two natural frequencies plus the input frequency. This was a special frequency, zero frequency, where it only produced the natural frequency. It doesn't produce the forced input frequency. That's what's special about it. Yes?
From a problem-solving standpoint,
right.
would it be better just to find the zero first, and then find the, just add on the forced response because we have the function
From a problem-solving so the question is, from the problem-solving standpoint, would it be better to do the deal with this, find the 0 and then do the add-on? This is more of a conceptual thing. From a problem-solving perspective, you can always plug it in and see what the response is and do partial fraction expansion, right? That's kind of like a very powerful, general, catch-all thing, right? Now, this is a more conceptual thing, right? I mean, you can use it, and there are certain special cases where this is useful. But for a general problem, it's not. But this is a conceptual thing because this leads you to. This example is important because it shows you what zeros are. Because later on you may say, wait a second, how is it possible that I have a system that I drive it with a certain frequency and it doesn't produce that frequency at the output? And this is an example, and you can basically do it with different kinds of things as long as you have the appropriate zeros at the right frequencies. Yes.
So poles in this case are 1 and 2.
Right. Well, -1 and -2. Right. The roots of the denominator, and the 0 is -3. So I'm going to actually get to the poles. So what if I so let me ask you this question. So let's do another one. How about e to the -2t u of t? What if my input is e to the -2t u of t? What happens? What's my forced response? What happens there to my forced response? According to this. According to this calculation, the output is h of -2 e to the -2t u of t, right? Which is what? What is h of -2t? Infinity, right? And so is this correct? Is that the output? Is that not? What is it? What's happening? Go ahead. Well, kind of. Not exactly. So you're saying resonance, but it's not. This is not. Did you see that question mark I put up there? There was a reason there. They put that question mark. You will see in a second. But can I even do this at this particular frequency? No. Alex is shaking his head. Why? Why not? Yeah.
Because it violates your condition.
Exactly. I'm violating an assumption I've made earlier. You saw this? Remember this? So I violated an assumption that I've made. So I can't calculate my response this way at those frequencies. Very good. So now what happens here, if you think about it, is so this is not the way you calculate it. But does it mean that there's no calculation? So does it mean that there's no response? No. If you want to calculate the response, this is your system operator. So you basically say p plus 3 over p plus 1 times p plus 2. And this operator, the input operator for this is 1 over p plus 2. So I get this squared. And I can do a partial fraction expansion of this, and I will get what I get. Right? I can do it just if you want. Just like the partial fraction expansion of that is actually 2 over p plus 1 minus 2 over p plus 2 minus 1 over p plus 2 squared, which gives you 2e to the negative t minus 2e to the negative 2t minus te to the negative 2t u of t. So this is a perfectly reasonable, rational, it's not rational in the general sense of the word, not in the mathematical sense of the word, response. You see, so that's basically y of t. And look at the frequencies you see. So you see the natural frequencies, and you also see these t terms. This is coming from that being excited at this natural frequency, right? When you're exciting it at a natural frequency in this form, it produces something like this. Yes?
So are the frequency responses non-continuous? Because
Yeah. Yes, yes. They can, yeah, they would be non-continuous at those frequencies. Those are the poles. At pole frequencies, it's not continuous. Those are the roots of the denominator, yes. Correct. Now, you earlier mentioned resonance. And resonance is related to these natural frequencies, but in a different way. That happens for a pair of complex conjugate poles, when you have, for example, an LC circuit. Not two poles of the kind of like the RC type. Right? So we'll see examples of that. So it's not unrelated, but this is more general again, because we are dealing with complex frequencies. The complex frequencies can be regular exponentials with real coefficients, or they can be cosines and sines, or combination thereof. So your answer was not incorrect, but that applies to a subset of general responses where this one is not that subset. You could think about this as some sort of resonance. But then again, I don't think you should necessarily. All right, any questions? Okay. So this development actually brings us to the next thing that we want to talk about, which is, a related thing, which is the concepts of poles and zeros. As we discussed, the roots of the numerator and the roots of the denominator of a system. So let's say you have a system function, right? Or transfer function. If it's a rational system function, and we will see that in most general case, they are not, for most general systems, they are not necessarily rational. But you will see that, but for lumped system, they are. Now, in fact, you have one of the problems in this set that shows you how it transitions from a lumped system to a distributed system. And when that happens, you will see that the transfer functions that you get become irrational functions. So that's one of the problems that you have, one of the packet problems that you have. So it's a practical example. And I'm not going to say more because I want you to go through it and we'll discuss it later. So now, but in general, if it's a rational function, you can write it as a numerator and a denominator, right? And each one of them have their own roots. So you can actually write them as s minus s1, let's say s minus z1, s minus z2. So these are the roots of the numerator, s minus zm over s minus p1. Okay, now here's one thing that starts messing our notation. So you remember p was the p operator, right? Everywhere when you look, p is also used for poles. Now, that's why I preferred the D, the capital D, because then you wouldn't have this confusion, etc., etc. So for now, I'll show them as R1s and R2s, roots to Rn. But almost always they're shown with P's, P1s, P2, P3. But then that would create additional confusion of notation. But we're trying to keep things consistent. So you understand what it is. So you can write it this way, right? Because according to the fundamental theorem of algebra, I can factor these in terms of first order terms with, complex coefficients. So there's another way to write this. You can write it as, you can factor what we call the DC part of it and write it this way. You can write it as 1 minus s over z1, 1 minus s over z2, 1 minus s over zm, and write it as 1 minus s over r1, 1 minus s over r2, all the way to 1 minus s over rn. Now, the advantage of this form, I prefer this form because it shows that this part of it, if you set s to 0, goes to 1, and what you're left with it is the transfer function at DC, at extremely low frequencies, when things don't change. So this is like the DC gain of an amplifier, if you will, or of a filter, or something like that, what it does at low frequencies. And if your system is a low-pass system, this is a good form. There are other forms that are nice for high-pass systems and all those things, but this is a classic low-pass filter form, and it's a useful thing. So now the roots of the numerator, So roots of n of s are called poles, as we said. And roots of the denominator, are zeros. Yes, yes, thank you. So the roots of the numerator are zeros, and the roots of the denominator are poles. I'm glad that you guys are paying attention to catch these things. I would have liked to claim that I do these on purpose so that you catch them. So zeros are essentially S's, the frequencies at which the system, so at zero frequencies, S being Z, one of the Zi's, it basically makes the H of S 0. And for S being equal to one of the pole frequencies, then you get H of S going to infinity. So the transfer function blows up at those natural pole frequencies. So this is all nice and good, and all that kind of stuff. But let's do something that this is a useful way to think about it, and it's an important way to visualize these things. So, by the way, there's a notation for showing the poles and the zeros. So let's say we are looking at the complex plane. So this is a two-dimensional plane. This is the sigma axis, the real axis, and this is the j omega axis. So we are in the S plane, right? Any point on this plane has a sigma and a j omega, so it's sigma plus j omega, so any point describes a complex number. So the poles and zeros, the roots of the numerator and denominator, can be shown at different places. This is interesting. The line was straight, and then all of a sudden just hopefully a little bit better. Okay. So now let's start with something very simple. So what we are trying to do is to find the impulse response. So what we are showing is the impulse response of a system with certain poles and certain, starting with the poles first, and then we'll see what how the zeros will get into the equation. By the way, we show the poles with x's. So if I put an x here, it means that the system has a pole here. And we show the zeros with O's, like zeros. So if I show this, so first of all, if I say this describes my system completely. Is this an actual real system? So is this a real system with real coefficients transfer function? Can you have a system with real coefficients that has just this one pole? No. For it to become real, what do I need to do? Yes, I need to have a complex conjugate one too, right? So, but this is a real system. Unless it's on the j omega, unless it's on the sigma axis. So this is also a real system by itself. This is also a real system. This is real system too. Okay, so I can show my poles and zeros that way. So what I will do, we'll start with zeros at different poles at different places, systems, and we are trying to show the impulse response of that system. So let's start with the simplest of them all. What is this system? If I show you this diagram, what is the associated system function or system operator or whatever? Yeah, that's a response. So what is the system operator first? 1 over p, right? So the system, or 1 over s. So this would be 1 over s. H of s is 1 over s, or h of p is 1 over p. And its impulse response would be what? U of t. So this guy has an impulse response that's 1, the u of t. What if I had a system whose pole was just, so this is not both of them, it's either or really, but I'm just going to put all of them on the same plot. So if I didn't have this and I just had that, is that a real system? Is it something with real coefficients? Yes. What is the system transfer function or system function? If this is at some point, let's say, I don't know, negative r. What is the transfer function associated with this? 1 over s plus r, right? Because that's the root of 1 plus s. So this would be 1 over s plus r, because the root of this would be negative r. So, but that being 1 over s plus r, what is its impulse response? E to the negative r. So the impulse response of this thing is something like that. E to the negative rt u of t. This is u of t. What if my pole was farther out here? Just that system. Again, forget about those by itself. Typically, you show this plot for one system. So I'm just like superimposing these plots for different systems on top of each other so you can see their impulse responses. So what would that look like? If it's like this, let's call this R1, negative R2. What would it look like? Another exponential, but would it be decaying faster or slower? Faster, right? Think about it. R2, the absolute value of R2 is greater than R1. Or is it faster or slower? It's faster, yeah. So this is e to the negative R2t u of t. And if I go very far out, essentially it becomes very quick. The impulse response becomes almost the impulse, right? Now, how about if I'm going in this direction? What if I have something here, R3? Right. So now this is going to be a growing exponential. Actually, these are, yeah. So this is going to be RT u of t, R3 u of t. So it's going to be an exponential. And if I put one down here, what would that look like? Oops. That looks like a double pole. But so how would that look like? What's the impulse response of this system? It's an exponential that just grows faster. So you see the transition. And you see this should make sense because this should be continuous because as you bring this closer and closer and closer, this pole, like all three, look at this. As you get closer, it should asymptotically, when you get very close to this point, it should almost look like that. Why? Because it's so slowly growing at that point that essentially it would be very slowly going. So when you get it to 0, essentially it becomes flat. And when you go past, and when you take this and bring this, if you have a pole very close to here, this is so decaying so slowly that essentially it's just converging to the step. So that's for real poles, single real poles. What if I had complex conjugate poles? Let's say imaginary poles. Right? First start with imaginary poles. Poles on the j omega axis. Obviously I can't have one, right? So I can have a pair of poles here. So this is really a second order system because it has two poles. What is the impulse response of the system if I just had those two poles? Think about it. What's the system? Its system is 1 over.
If the height is like.
Yes, it's a sine. Yeah, it's a sine. Let's say this is omega 1, right? Really, it's j omega 1. So I should have picked these as sigmas. But anyway, so if it's this is going to be a sine u of t. So it's basically sine of omega 1t u of t. It's the impulse response of these two together. Now, if I'm farther out, let's say I have another pair here. So this is negative j omega 1, negative j omega 2. So if I have another pair here, how would that look like? Yeah. Yeah, it's a sine with just moving faster. It's a higher frequency sine. Okay? So that's fine. That's good. Now, is this really, so let's see. If I bring these, so let me ask you a question and see. This requires a little bit of thinking. So I argued that these things in the limit should reduce to each other, right? So as I start bringing these closer and closer, what happens? This becomes slower and slower and slower, right? Sine. So when I get to down here, and I have these two here, does it reduce to that? Does it? It's going to be a very slow sine, right? Does a real slow sine reduce to that? The real slow sine looks like this, right? It starts from 0. It doesn't start from 1. It doesn't jump to 1. What's happening? Why? Why doesn't it reduce to, when we take these two and bring them close to each other, why doesn't it reduce to this u of t? Why does it become like that? Is this the same system? Ask yourself that question first. Right, it's two poles, not one pole, right? So it's when you get them here, it's equivalent of 1 over p squared. What does 1 over p squared do? What's the response of 1 over p squared? It's te to the negative, or basically, well, it's a t, it's a ramp, right? So in the limit, it's just a ramp, right? So in the limit, you can see if the sinusoid is moving so slowly, if you look at it, it should look like a ramp. And it does. Now, if I wanted, so you say, well, wait a second. No, but if I can actually make it a little bit more interesting. So now let's say you have this system plus a 0 at the origin. So the system has these two poles and a 0 at the origin. What is the response of that system? That's it, p in the numerator over p squared plus omega squared, right? What does that give you? Cosine, right? What does cosine? So this is a sine. The cosine response looks like this. And as I reduce the frequency, it becomes more like that and more like that. And in the limit, it becomes a step, which is what you get if you take these two poles and you have a 0 at the at the origin. By the time you get to the origin, the 0 cancels one of those poles because they're right on top of each other, right? When I say 0 cancels one of your poles, it means that p plus 3 over p plus 3, they're going to cancel each other if they're at the same frequency. For example, not p plus 3, it's going to be p plus epsilon. Right? So it makes sense, right? It should reduce to a ramp if you have just a pair without that 0 here. And it does. Okay, so that's fine. Now, but what I've covered so far is a very, very, very small subset of all the possibilities. Right? You know, mathematically, they say it's a measure 0 subset of all the possibility. If you have studied measure theory or Riemann integrals or things of that, Lebesgue integrals. Anyway, so okay, now what are the other things? The other things are things that can happen anywhere else other than the two axes. So what would I get if I have a pole here, a pair of poles, obviously, here? That's my system. So what is that? What is the impulse response of that? So those things correspond to things, for example, what I just showed is like an, it's like omega 0 squared, omega 0 over p plus sigma squared plus omega 0 squared. right? And those are, what kind of response do they generate? Decaying sinusoids, right? So if I have just this, it would be a decaying sine or a decaying cosine? Decaying sine. If I had the 0 at the origin also, that would give me a p. Or a 0 somewhere else, it can give me even p somewhere. So here, so decaying sinusoids, right? So, and what's the decay rate? If it's right on top of that, for example, I should have chosen this to be sigmas, but anyway. Yeah, let's make them sigmas. Just. Right? So it's a decaying sinusoid. The decay rate is determined by the real part. The frequency of the sine or cosine is determined by the imaginary part. So now if I have another one, another pair here and there, what do you expect? How would it look differently from the other one? Go ahead. For the higher frequency of the sinusoid and faster decay, exactly. So it would be a higher frequency sinusoid decaying faster. So that's what those two poles are. Now what if I have a pair of poles here? What would it do? What would they do, I guess? Right, so you have a growing sinusoid, right, of a certain frequency. And why are these so important? Because of partial fraction expansion and fundamental theorem of algebra, these are all the responses you can get from rational functions. These are it. This is it. It's just combination of these things for linear system. All right, any questions? Okay, so now I'm going to have a simple, okay, we're going to do a simple aside. And we'll talk about it later, but this is just like a simple thing. So now imagine so this is completely different from that apparently, but it will come in. So let's say if I tell you, what if my input x of t is just e to the st? Just e to the st. How would you calculate the response of a system if you know it's, if I told you its impulse response is h of t? How would you do that? I mean, the basic method, right? It's convolution. So this is an interesting thing. It's an opening to something else. Just want you to see something here first. So how would you do that? Y of t is going to be x of t convolved with h of t, right? So I can write this as a convolution, use the convolution integral. I would get h of tau, x of t minus tau, d tau. By def. Sorry? No, it isn't. That's what I'm. So yeah, there's no u of t. Good. No, good observation. Important one. This is different. This is general. So yes. So this is different from what we've been doing so far in that sense. It's not a one-sided function. It's a two-sided function. Okay. All right. So now I plug that definition of x of t in there. So I get h of tau e to the st e to the negative s tau d tau. T is not a function of, it's a constant as far as this integral is concerned, right? So this term is not a function of tau. I can take it out. I can write it as e to the s tau I'm sorry, st, not s tau, st integral from negative infinity to positive infinity of h of tau e to the negative s tau d tau. So you can see that the response of the system also is of the form e to the st weighted by this thing. Right? That's the scaling of that thing. So I can write that thing. I use this notation for that thing. So whatever that object is, that number is, it's a function of, it's going to be a function of s, right? We show it as h of s e to the st y of t is going to determine what the weight of this thing is. This operation that we performed on the impulse response has a name. Does anyone know what this name is? Its name? What is this called? Laplace transform. That's what Laplace transform is. That's it. So Laplace transform is essentially defined as so this is Laplace transform. So essentially Laplace transform is evaluating the system response for an input that's e to the st. The weight of the forced response of a system with an input of est, e to the st is Laplace transform. There's a very, and you will see it's a special case of what we've developed. The tools we've developed are more powerful mathematically and more general. Because Laplace transform has all these issues, if you will, with the regions of convergence and things of that sort. You have to worry about it, if it's convergent this region, doesn't it? Then you apply it to one-sided functions, then it becomes what, this is the two-sided Laplace transform, more accurately. Then if you apply it to one-sided h of t's, then you will get the one-sided Laplace transform, which is integrated from 0 or 0 plus. And that's why when we were talking about u of t, as I said, when we were defining u of t, I said, well, the value at 0 does matter only in the Laplace transform because it defines a limit. Is it 0 plus or 0 minus or things of that sort. The way we defined it, it would make it consistent with the 0 plus definition. So we have what we developed, that the operator system completely subsumes the Laplace transform. It's more general because you don't have to worry about those regions of convergence the way we need to worry about it in the Laplace transform. So we'll talk a little bit more about Laplace transform, more as an aside than other thing. But we'll do that next time. Any questions? All right. Okay. Well, I guess I'll see you next time.